Thank you for coming. I'm going to talk today about analog design. This is how I've spent my career, is doing analog mixed signal designs on logic processes and generally being given, fairly accurate process models sometime after the product has taped out. But it makes it interesting. So just I'll try and provide an introduction to the problem, talk about scaling, variation, statistics, methodology. Methodology is really what has made it possible for us to design these very large chips. And so what are the implications of needing to follow methodologies? You've seen some of that already. Analog is a little different than digital, but there are common factors. So I just thought I'd start with, why analog design? We live in a world where everyone hears about digital, Digital technology is what makes it all possible. So why do we even waste time on this analog stuff? Well, the issue is reality is analog. And we have to deal with reality. So you've got power. You may have to do voltage conversions, temperature measurement, randomness. We have random number generators because it turns out security people like keys that are hard to guess. Phase lock loops to generate clocking signals, wireline I/O. When I have wires where the length is, significant as compared to the wavelength of the signals, I have to worry about impedance matching and questions like that. And keep in mind that the wavelength of the signals is not the bit rate, but it's related more to the edge rate. And so edge rate control becomes important. Wireless RF configuration. Again, we have fuses in these technologies, and digital guys like to think of a fuse as something that gives you a 1 or a 0. But the reality is, if you get down to the device level, the difference in resistance of the fuse between a programmed fuse and an unprogrammed fuse might be an order of magnitude or 2. And if you draw large amounts of current through it in order to get a significant voltage, of course, you change the state of the fuse and defeat the whole problem. So all these are analog problems that we need to deal with. And why do we do it? Well, we do it because the digital designers are incredibly productive and valuable if you allow them to make believe that the world is made up of ones and zeros and well-defined time intervals. So we want to keep the digital designers operating in this imaginary world because they deliver very good things. So, has this changed over time? This is basically, my career doing processor design. I started in Intel at '91. And at that point in time, there wasn't much in the way of analog circuits. We just had, a phase lock loop and I/O. But over time, the number of analog circuits, the number of unique analog circuits has grown. The area that we're spending on these circuits has grown. And these days, 40-ish different circuits. PLLs, high-speed I/O, both single-ended differential, voltage regulators, power management, configurations, all kinds of stuff. On average, we've grown about 4 new circuits. And perhaps more importantly, 2% of the die area switching from digital to analog each generation. And so as we push further ahead, analog becomes more important. We need to have those enablers in there. And then if you look at, in general, the requirements have also gone up. Phase lock loop, the frequencies we're expecting out of these things have gone up in order of magnitude. The jitter constraints on the PLL in general have gone down somewhat more than scaling. The digital thermal sensor, DTS. If I go back to when we first introduced one of those, it was a really simple circuit. It had a trip point of 140 degrees C, plus or minus 15. The whole point of it was to make sure that if the chip started getting too hot because something went wrong, that you turn it off before it makes smoke. These days, the digital thermal sensor is part of a power management system. And so it has to operate from, minus 10, sometimes minus 40, all the way up to the high end, 1 degree C resolution. And this allows the power management system to understand what's happening on the chip. If I'm operating very cold, as Saurabh alluded, there are inverse temperature dependence effects. So if I'm really cold, I may want to bump the voltage up to overcome those effects. If I'm really hot, I may want to drop the voltage and frequency to control temperature. And so it's become a much more complicated situation. I/O has gone up in frequency, and again, this somewhat understates the problem. That 400 megahertz I/O back in 1997 on Deschutes was actually on a processor that was designed by Intel, talking to a memory that was designed by Intel, on a card that was designed by Intel. Now when we're doing this 6.4 gigatransfers per second, we're not designing any of the cards here, the boards. That's entirely up to the end user, so the modeling becomes more challenging, trying to make sure that you're delivering something that can work in a variety of systems and continue to work well. So, and I want to talk about clocks as being analog, because clocks, you know, they're all ones and zeros, looks kind of digital. But the reality is they're analog in the time domain, and we have to worry about this because PLL-generated clocks do not deliver, you know, very precise timings in the way we would like them to be. They jitter, the edges move around, and in general, you can control that. But it costs you power to place the edges more accurately. And as a general rule, nobody wants to spend power. So you want to place the edges, you know, as precisely as you need to and no more precisely because you don't want to spend that power. And it becomes an issue because when we're looking at systems on chip these days, there are many clocks on the chip. And you have signals that start in one clock generated by one PLL and are communicated to another clock generated by another PLL. And from the point of view of the logic designer, the less restrictions they have, the better. So they'd like very low jitter clocks that make it very easy to do the crossings, but they don't want to spend the power. So it becomes an optimization problem where you're trading off some complexity in the digital domain for power in the analog domain. Next, I'd like to talk about scaling. You know, part of, you know, how do we get here? Where are we? Where's it going? You know, it really goes back to Moore's Law, which we've heard mentions of earlier. You know, I'm from Intel, I have to mention this. But I do find Moore's Law interesting because Gordon Moore, you know, made a really simple observation. He drew this graph, which is the relative manufacturing cost per component versus number of components. And what he found is when you looked at an individual technology, there was a sweet spot. If you had too few components per chip, the price was high because you have overhead. You have, you know, bond pads, other stuff you have to get in there. On the other side of the curve, if you have too many components, yield becomes problematic. And again, the cost goes up. And so in any given technology, there's a sweet spot. And then the magic of Gordon Moore's observation was the sweet spot goes up over time. And so if you want to be the most cost efficient on any given technology, the number of transistors tends to grow every generation. And that's really all there is to it. So at its root, Moore's Law it's an economic law, a financially driven thing, as opposed to a purely technology-driven one. You know, the performance questions, things like that came along later, but he's really talking about cost efficiency. And so, you know, that's what we have there. That's taken us to this, and these are Intel data points, because those are what are conveniently available to me. But you can see we've been pretty close to a 2x increase every 2 years in transistor count for a rather long time. Perhaps what's more important about this is, you know, because people don't buy transistors, is that as we've been raising transistor counts, we've also been increasing the functionality and raising the power or improving the power performance trade-off as we go along here. Because those are really the attributes that people care about in the products. You know, whether you've got 100 transistors or a billion, who cares? It's the behaviors you're getting out of it. So, now I'm an analog designer. How does all this scaling stuff apply to analog? And the answer is it affects us in a couple of ways. One is the number of VTs I have in my power supply has been shrinking. When I started at Intel, we were still doing 5-volt chips. And so we had, you know, 8 to 9 VTs. And so you could stack up your VTs. You could do very interesting analog circuits. And the power supply voltage was high enough you could make it work. But as we have scaled down the supply voltage, we've also scaled down VT, but not nearly so quickly. And frankly, it's hard to see here along the bottom, but it's been kind of flat. And so the number of VTs in the power supply has been shrinking, and this seriously constrains what you can do in terms of analog circuit design. And so a number of those circuits that were workable, were usable back, you know, in the 800 nanometer days, just don't work anymore. if I were to run the power supply voltage up high enough to make them work, I start running into reliability problems. I have another challenge here, which is that in general, there's this assumption that I will scale the LE of the device. And in digital, that's wonderful. I make LE shorter, my device gets faster, smaller, less expensive, everything is good. Not so much in the analog realm. Whether I'm looking at the GM or the output resistance of the device, as I scale the LE down, the performance of the device gets worse. And I can put all these together and find that I can look at signal-to-noise ratio scaling. And nominally, I'd like my area scaling factor of a circuit going through one generation of technology to be around 0.5. That's what makes all the digital circuits, it's where they like to be. But if I'm looking at an analog circuit, if I'd like to maintain constant signal-to-noise ratio, and I'm trying to scale LEs, in fact, I have to scale the area up, not down, in order to maintain constant performance, which tells me to the first order that simply taking the circuits I have on technology n and scaling it by simple shrinking to n+1 in the analog realm is not such a good idea. So I have other issues. Reduced operating range. In general, as my supply voltage goes down, the magnitude of signals I can bring in go down. The noise in general doesn't scale. So my signal-to-noise ratio, again, it gets compressed. This is what leads to the issue of needing to make circuits larger to overcome that. The other thing is low overdrive. We all talk about VT mismatch. And if you look at VT mismatch over time on devices, it tends to get worse. But the reality is, even if you could hold the VT mismatch constant, by bringing down the supply voltage, you're making the impact of VT mismatch worse. And so that hurts us. You may even get in a situation where either because of variation or temperature, it's hard to even keep the devices operating in saturation. Finally, weakly off switches. As I say, I've spent my whole career at Intel designing analog circuits in parallel with the process development. And one of the things that has helped me keep my sanity is to build options into the circuits so that if you're expecting the process to be over here and it ends up over there, well, if you've got some options built in, you can try and move it back. That invariably involves putting switches in the circuit. And when the switches don't turn off very effectively, that means that they're probably loading down some critical node in some way you really would rather they didn't. So, all of which leads us to mixed signal design. So the lack of scaling in classical analog circuits means we really need to bring in more digital techniques. So there are digital phase lock loops where typically the oscillator is analog, but everything else in the system is now a digital circuit. So my whole loop filter has become digital. Sigma delta and successive approximation, analog to digital converters, dynamic element matching, correlated double sampling, tuning. Digital calibration has really become critical to the functioning of analog circuits and to get them working on these leading edge processes. And so, the good side of the fact that we're getting into trouble with scaling the analog because digital is driving where we want to be is that we can take advantage of those same digital techniques to make analog more scalable. Now, there are issues there. Sometimes applying these techniques, if I do simple digital oscillators from my PLL, I actually hurt my power supply rejection ratio, which means voltage regulators become more critical. Those voltage regulators got harder to design. But perhaps more subtle, I have to draw from both the analog and the digital design methodologies in what I'm doing, and I have to put them together in the same subcircuit. And that's not a free lunch. So one thing I learned early, I went to graduate school and I first started taking courses about design, and of course you learn about analysis, not design. When I started working, the thing that I learned was I figured I'd be doing design, but the reality is design is 90 to 95% validation, making sure you didn't screw it up. Well, when I'm mixing analog and digital circuits in very close proximity, the challenge that I have is they use different methodologies. if I were to use the analog methodology for validating these circuits and use simple circuit simulation, what I find is when I'm throwing the digital circuits around it, the number of transistors is going through the ceiling, and the run times that I would get from circuit simulations explode. It's really not a viable approach to take the entire system in a circuit simulator. But conversely, the RTL, register transfer level tools that work very effectively in the digital realm, how do I explain impedance to a register transfer level model that only understands ones and zeros? So instead, we end up needing to use mixed signal tools that somehow meld these two things together. Newer techniques, newer approaches. And there's also a testability question. As I embed these analog circuits inside the digital, how do I get to them? For the I/O circuits, it's not quite as troublesome because in general, they're I/Os. They come out to the edge of the chip. Access is pretty good. But not all those circuits I listed are, in fact, I/Os. So how do I either de-embed the circuits or put appropriate design for testability hooks inside so that I can actually get access to the parameters that I need to look at to test these things? So my validation, my test problems become more challenging. Then there's variation, which we're all well aware of, but it significantly impacts what I'm doing in analog design. So threshold variation, no surprise, roughly proportional to 1 over square root of area. C2 is, for whatever reason, the labeled coefficient that we put on this coefficient at Intel. Process improvements provide some relief, but the reality is, you still suffer from scaling. Let me just explain this a little bit more closely. If I just plot sigma VT versus 1 over square root of area, you get numbers like this, and we draw a line through that and find that, in general, this is a good description of the variation that you get. That C2 coefficient is process dependent. That's the good news. The device engineers are out there trying to make it better. However, if we look at how this scales over time, and the data's a little old, but fairly representative, what you see here is, scaled back, normalized to 180, you can see that our C2 coefficient has scaled this way over time. What happened here, going from 90 to 65 nanometer technology, is we basically hit the limits on silicon oxynitride scaling on the gate dielectric. And so the gate dielectric didn't scale. As a result, you didn't get any improvement in the C2 coefficient, and we found we really needed to switch to high K metal gate. So this looks good. You can see that over 4 generations, we got a 40% reduction in the C2 coefficient. Very nice. But the reality is the C2 coefficient is based on a fixed size device, but nobody wants fixed size devices because Moore's law is an economic law. We go to these new technologies to make more money, to make them more cost effective. That means to shrink things. So whether you're talking about a minimum size device or a nominal, an average size device, the reality is when you put the combination of scaling and process improvements together is that variation goes up. And that makes it interesting. Noise is another question that we often ignore on the digital side of the house, but on the analog side of the house, it's a first order concern. And there's 2 factors we tend to look at. The first is you've got thermal noise, white noise, and if we look at how it scales, you find it scales roughly L over W. It depends on the channel impedance, and that scales fairly nicely. And so to a first order, the white noise, thermal noise aspect of your design scales pretty well from one generation to the next. On the other side, there's also 1 over F noise, flicker noise, and in general, this does not scale so well. It behaves similar to the variation concerns. In fact, you can see here we've got the area term of the device multiplied by Cox squared, and just as in the case of the C2 scaling in matching, the effect of area reduction overwhelms the improvements you get from oxide scaling, and the net is you end up somewhat worse off for 1 over F noise. And what this means is that the dynamic range you can utilize for your signals is shrinking every generation. So if you're sticking with purely classical analog techniques, this is not your friend. yet another reason why we want to go after analog mixed signal approaches, using digital techniques to also make sure these circuits scale. Statistics is something I often run into. People talk about statistical design and they say, 3 sigma. 3 sigma design is good. That's what I should be doing. Because a 3 sigma design yields about a 0.1% failure rate. Of course, where you get in trouble is that it's a 0.1% failure rate for whatever it is you're designing. If you're designing an SRAM cell and a 3 sigma SRAM cell fails, you got a problem. So we really care about the failure rate, the yield for the entire product, not just for the individual subcircuits. So when you're designing an individual circuit, you really need to think about, what do I need to do? What yield do I need to get on that circuit? So you need to look at, what proportion of the product is being analyzed. What are the number of instances of the circuit? If I'm dealing with an SRAM circuit, we get large numbers of bits there. And depending on the probability failure that you're willing to live with, you can figure out how many sigma I want to look out in the distribution. And what I find for most of my I/O circuits, you want to be somewhere in this kind of range, 4 to 5 sigma. SRAMs can often get down to this level. But the 4 to 6 sigma range, when you're talking about analyzing your circuits, are very interesting. And that's significant because, for example, if you use Monte Carlo techniques, you never see 4 to 6 sigma. You just won't get there. So you needed a little more intelligent analysis of variation. But another thing this brings up is distributions. Do I have the right distribution for the parameters I'm looking at? We have a real tendency to assume things are normally distributed. I have Gaussian distributions. But sometimes other distributions are more appropriate. And I'm going to talk at somewhat more length, in particular on the Poisson distribution, because sometimes that's appropriate. For example, Poisson talks about the number of events in an interval. And this could be the number of dopant atoms in a channel. It could be the number of traps in a channel, in which case you're talking relatively small numbers. And a Poisson distribution is characterized by K, the average number of events. Well, how does that compare to normal? Well, if K is 10,000, kind of a big number, it actually compares pretty well. And you can see Poisson, the normal, they line up quite nicely. Of course, as I said earlier, I'm really interested in that 4 to 6 sigma kind of range. So if we put this on, missed the slide there, a log curve, this is what it looks like. And it's a little hard to see, but you can actually even here notice that there's a difference between Poisson and normal as I get out to the extremes. Not very big with K equals 10,000. But with K equals 1,000, you can see there it's maybe a factor of 3 on the extremes. If I get down to K equals 100, and you can actually see at this point that the Poisson distribution is actually a discrete distribution. If I have K equals 100 and I'm doing a design and I'm interested in 6 sigma kind of behavior, you can see on one side I have orders of magnitude of error. I'm on one side of the distribution, I'm over designing things. I'm worried about problems. My analysis tools, assuming normal, are telling me problems are happening 100 to 1,000 times more often than they really are. And on the other side of the distribution, I'm under designing. So it's really leading me the wrong direction. And if you get down to really small numbers, you can actually find that, gee, if K is 10, I'm never going to see 4 to 6 sigma on one side of the distribution. One side of the normal distribution. That just physically doesn't occur. So you want to pay attention to your distributions. Also, log normal. We heard talk earlier this morning about using the median device. And in fact, when I talk to my device engineering guys, they love the median device. Well, if I look at an actual distribution, we have a distribution and we have a target. And the median device just so happens for the performance axes, the median is the mean, is the mode. Life is nice and simple. But when you are looking at the leakage axes, it turns out that the circuit designers really care about the mean device. And on a log normal distribution, the mean is systematically larger than the median. And they care about the mean because what they're going to do is they're going to build a whole chip and they're going to measure it and they're going to say the power of the chip is higher than it should be given the nominal device you told me right there. And the fact is, you will never get a chip that represents that point there, because the statistics of the situation tell you that you want the mean on the one axis and median on the other. So you want to make sure you communicate this well, but get the right distributions in here. So the difference between those is significant. We've all run into this. So design methodology, just to get back around to what I mentioned to earlier. How do you do design? Design of a chip is done through a very iterative approach. We start from a very high-level description of a chip, and then end up with layout. Layout drives the generation of masks, and you go and build it. And often you start, PowerPoint engineering, some concept that is not executable, just written down, but that provides your initial description. But then we tend to go through this level of description where we go from behavioral to structural to schematic to layout. And this actually applies to analog and digital, although the details differ. In a digital realm, I'll have a transaction level model for my behavioral model, where I just describe the sequence of things that happen. I fetch data from a memory, for example, and that's a transaction. And the transactions are, I assume they're in sequence. And so this is the programmer's model for microprocessor. One instruction is executed, starts, executes, finishes. The next instruction starts, executes, finishes. And you can actually simulate the way programs execute correctly in that manner. But in fact, it's not equivalent to what's actually done in the hardware. Modern transaction level descriptions are executable, but it allows you to do a lot of optimization functionality checking. It simulates very quickly and effectively. Next, we have a structural model. The structural model, gives you some idea what the structure of the system looks like. It turns out that register transfer level descriptions here are used. You can tell structures, registers, adders, subtractors, buses. In general, register transfer level is what we call cycle accurate. So that if you want to know if I run this particular sequence on this particular piece of digital logic and I want to know how many clock cycles it will take to finish, I need an RTL level description, a structural description, not a transaction level description to answer that question. Interesting aspect is that with RTL, I can actually compile this and build it on a field programmable gate array. So I can start doing validation on my system at a much higher level of performance by actually emulating the system there. Don't really have a good structural level equivalent in an analog system. Schematic and gate level, describes the transistors, the connections between the transistors. Here I get timing information, nanoseconds, picoseconds, actual frequencies of operation. And so I get precise timing, but the accuracy depends on getting good parasitics from the layout. And we heard that earlier. You want to extract the layout effectively to get good information here. And then finally you have layout. The idealized shapes. And I say idealized because as you go through optical proximity correction, of course, they change shape. We heard earlier that there's a time when SPICE consumed a lot of CPU time. Actually, as we go through these hierarchies, somewhere in the 90s, it was actually the RTL that consumed much more CPU time than SPICE simulation in making chips. And these days, it's the optical proximity correction that consumes the overwhelming fraction of the CPU time. So the layout's a design abstraction that's closest to the final product. So how do we get all this right? Well, we have to check things incrementally. And so some checking in general, when I say checking, I mean I compare one abstraction level to the next. So LVS compares my layout to my schematics and makes sure that the two match. In general, my checking techniques can be equivalence checking or they can be testing based. So equivalence checking, when I compare layout to schematics, I actually extract structures out of the layout, compare them to the schematics, one for one, make sure they match identically. When I compare schematics to the structural implementation, it's actually formal Boolean mathematical proofs that make sure that the schematics are functionally identical to the RTL. These days, nobody has the technology that enables a behavioral to a structural comparison in terms of equivalence checking. So that checking is all done through testing, meaning I write programs, I write instructions, I run them on the transaction level model, I run them on the structural model, and make sure the answers come out the same. And if I was clever enough to test all the cases where mistakes occurred, I'm good. The reality is you can never exhaustively test your way to equivalence. And so there's always some chance that you've missed something there. So ideally, we'd like to use formal methods, not always available. But this checking is critical to making sure you get it right. Now, if I look at the analog case, and the reality is I need analog. Analog circuits use the same general flows. I mean, the high-level specs are generally not executable. But I have some behavioral model. I have a system that's supposed to sample at a certain rate, have a certain bandwidth. I know what my constraints are, but they're not executable. RTL is I don't have a good structural level equivalent for my analog circuits. And then I get down to the schematic level. And I don't have formal verification, but I do have behavioral descriptions I can utilize in AHDL or Verilog A or one of these. And another just side note, the layout productivity is quite low. So if we could do something about that, that would be great. But in the digital domain, I have this equivalence checking. I can do formal proofs of equivalence. And a lot of this is simply because digital circuits are digital. They're quantizers. And so if I have little bits of noise in my input, if my gate strength is a little stronger or weaker than it intended, every digital gate is a quantizer, and it makes that variation go away. And that's what allows me to do these proofs of equivalence. Whereas in the analog circuits, all of these things accumulate. And if they accumulate to too great a degree, I have a problem. If they accumulate to a small enough degree, life is good. So the reality is that the behavioral models in the analog domain have to be cognizant of variation. But as a general rule, we do not have tools available that cleanly allow you to back annotate the real variation in the circuit up to these higher levels of abstraction. So as a design guy talking to people who have some influence on tools, there's a hole there. We really need to do better. Because without that ability, we're really not checking, we're not closing the loop back to the behavioral level models and making sure that we are, in fact, delivering the behaviors that were originally intended. And then there's statistical design. How do we abstract the behavior of an ensemble of circuits? You have to keep track of correlations in there. For example, if I'm laying devices out, and I have a source drain orientation sensitivity, that will systematically impact the way things work. And I don't want to treat those systematic correlations as uncorrelated. I'll get the wrong answer. But product data sheets, when you're looking at things, if I look at how the engineer's mind works, have always specified min, typical, max ranges on parameters. But suddenly when we're on chip, and we have control of the transistors, we tend to lose this. We don't back annotate this information back up to the behavioral level anymore. We really need to do that. And then just a couple other topics I figured I would throw in is uncertainty. We've heard people talk about some types of uncertainty already. Process targeting. When I'm co-developing my design and my process, there's going to be uncertainty because the device engineers may not be perfect in pointing out where the transistor lands. And I always have to say this to a design audience, but the fact is you don't want them to be perfect. The way the device engineers are perfect about delivering models up front that match what you get in the end is by being very, very conservative. And if they're very conservative, you're going to have a boring product. So the fact is, this uncertainty is a necessary fact of life. And then there's also retargeting questions. Sometimes you build the product, you get it out the door, and you find that, if I move the VT a little bit, if I move the LE a little bit, I actually get better results. And so you want to make sure that when you're doing your design work, you allow for all these kinds of uncertainty to not cause the product to break. There's also systematic but unknown effects. There are local density effects that are conceptually knowable. For example, when I'm designing my standard cell library, I could potentially extract every individual standard cell inside the environment it eventually ends up in, but it's not practical, but it's consistent and knowable. There are orientation effects. If I take a device and I flip it, it's a different device. As an analog designer, a digital guy will say, nah, it's still a transistor. But these things matter. And then there are truly random effects, random dopant fluctuation, line edge roughness, that are very local, truly random. What do I do with all these things? Well, often we take the different sources of variation, just combine them together and say, random variation. But should we? There's also a concept of skew corners versus random matching. So how do we do with that? Well, I look at this and I say, process targeting, that really falls very nicely in a skew corner kind of methodology. You can use skew corners to make sure that you stay alive over that. And the truly random effects are truly random. And so using Monte Carlo, design of experiments, various sensitivity analysis, you can look at those things. But what do I do with those systematic but unknown effects? And there I would say, I'm an analog designer. Any analog designer worth his salt will recognize that you control for these effects by managing your layout very, very carefully. And any digital designer who's paying attention realizes that you'll never get any productivity by paying attention to these things. You should just recognize they're uncontrollable and lump them in appropriately. So, there is no single right answer that fits here for everyone. So that there's actually not just the two approaches to dealing with variation, that skew corner versus random variation, but even the way you allocate different factors may change depending on what kind of design you're doing. And then productivity. The need to overcome the non-scaling idealities really limits the portability of analog design, makes it very hard to get from one process generation to the next. Restrictive design rules and interconnect rules, they're real constraints. We have to deal with them, but dealing with them is certainly challenging. And we need new ways to deal with those. You're probably not the people who are going to deliver that for me. So, in conclusion, digital design gets all the limelight, but the reality is the world's analog. We still need analog design in here. Scaling analog capabilities, not necessarily analog circuits, but analog capabilities is going to be critical to enabling new technologies to continue to be useful. And this really means more use of digital to deliver those same analog capabilities. And then design and analog productivity, layout productivity, improvements are needed. And then variation. Increasing device variation really requires device variation-aware design. Worst-case design, just not practical. Doing worst-case design these days, you're going to end up with something that is just so gold-plated, so bulletproof, that your competitor will eat your lunch. You won't be able to afford to build it. And skew corner simulation really doesn't highlight the impact of within-die variation. You need to use the tools appropriately. Perhaps most importantly, statistical design techniques are really necessary. Monte Carlo's nice, but if you've got a 1% problem, you're never going to spot it. Design of experiments is much better for that, but it bounds the size of the problem you can look at. The reality is these tools don't replace the need of design engineers to understand statistics. Unfortunately, many design engineers do not understand statistics. We need to work on that too. And finally, speaking as an analog designer, I'd really love to have a good way to abstract variation up to the higher level, get back to the behavioral level in analog design. And today that really isn't present. So, thank you for listening.